Hi. Hello. Maybe just. Hello. Yeah, thanks for the invitation to come and speak to you, and thanks for that very kind introduction. This is going to be a bit of a sort of old school talk, so there's like no mention of LLMs in here. So, I'll pause a moment and you can leave now if you're not interested in any of that stuff. Okay. Good. So let's see. Knowledge graphs. So I just usually like to start my talks with sort of intro to knowledge graphs, from my perspective, because it's a term that's bandied about a lot, means different things to different people. So this is what I mean by knowledge graph. So I'm not saying this is the only correct interpretation, but when I say knowledge graph, this is what I mean. So basically, it's a data structure which consists of a bunch of entities and values that are connected by directed labeled edges, and that's more or less it, really. Often we also think of this equivalently as just a collection of what are often called triples, which is just two of the nodes in the graph connected by an edge. And often, particularly in the sort of RDF world, the source of the edge is called the subject, the kind of target of the edge is called the object, and the label on the edge is called a predicate, but none of that is super important. So why is it interesting at all? Because in a way, it's a data structure for storing data, and we already had plenty of those, and in particular, relational databases is an extremely well-known and popular and useful structure for storing data. And in fact, this little example graph that I'm showing you here, I could equally well have put that in a relational database like this one. So why wouldn't I have done that? Well, I'm going to claim that knowledge graphs, the graph structure has quite a few advantages over this relational structure. Some of them are more subjective, some of them more objective. Subjectively, it seems to be a bit more intuitive. And I'd sort of support that argument by saying that one of the things we don't need here in order to understand what's going on is foreign keys. So if I look at the database itself, actually the individual tables are reasonably intuitive, but how everything connects together, I really haven't got a clue about that unless I know about this foreign key structure that is not directly stored in the data. Well, usually it's stored in some table somewhere, but it's not the immediate sort of data tables that I see. Whereas in the knowledge graph, more of this structure is captured directly in the graph. I mean, the other thing that was there in those tables, but maybe not super obvious, was that there was this little hierarchy structure at the top where I have architectural structure, and then I have these subclasses. Sorry, the text on here is pretty tiny, so I can't see what they are, but tower and building and so on, if I can just remember it. So this is more explicitly captured in the data structure. The other thing is that in the knowledge graph, we're typically using URIs to explicitly refer to so each individual entity in the graph has a unique URI representing it, whereas in contrast, well, there's quite a few advantages to that. One of them is that we can even kind of reference things in other data sources, knowledge sources. So, for example, instead of architectural structure, or as well as architectural structure, I could use this URI, which references that term in Wikidata, so that then I could maybe use some additional info from Wikidata to understand better what I mean by this architectural structure. And also, again, going back to our relational database, these kind of foreign key links, everything in there is strings, and things often occur in multiple places. Like I think Paris is in there multiple times, and I have to know about this foreign key structure, and I also then have to use kind of string matching to see where these foreign keys are really pointing. It's not a sort of explicit link as it is in the knowledge graph. Okay, and the other thing that's often put forward as an advantage for this graph data structure is that it's very flexible and extensible. So if I want to add information about architects, say, then there's nothing to stop me just adding that into my graph. I don't need to revisit the table structure and change that, which, as we all know, can be a bit of a nightmare in a relational database setting. One of the things I wanted to come back to later is about updating the data. So in particular, deleting edges from the graph can sometimes be a kind of an issue. And that was why I had this legacy edge in there about the UK being a member of the EU. It's not a mistake. I'm going to come back to that and discuss about deletion, which can be an issue, particularly if we're doing materialization-based reasoning, which is something I'll also cover a bit later. And another sort of subjective kind of thing is that another nice thing about graphs is that they're amenable to quite a lot of different kinds of querying. So we can think of a more structured query like the Sparkle language, which is very similar to SQL, but sort of more oriented towards the graph structure. But we can also think about things like locality queries. So what kinds of things are kind of near me in the graph? For structural similarity queries. So there are other bits of the graph that seem to have a similar structure to this bit. And again, you could do some similar thing with relational databases, of course, but somehow it's more natural in a graph setting. One of the things that relational databases offer that graphs don't immediately seem to offer anyway is views. And this is actually a really important thing in a relational database setting. They have a wide range of different uses, things like data integration and restructuring, but also security, optimization, and so on. And again, I'll come back to this a little bit later and mention how we can have views in a knowledge graph setting. Okay, so hopefully, A, we now know what I mean by knowledge graphs, and B, I've convinced you all that they're really wonderful and, a massive improvement on older style data structures. But there is, of course, nothing's just completely straightforward in computer science anyway. So there are several challenges that I'm going to talk about now. One of them is semantics, of course. So it was pointed out a long time ago that these kinds of graph structures sort of look intuitive. I already claimed they were, somehow intuitive, and nobody threw anything anyway. Maybe you were thinking, I don't really agree. And I think there's some justification for saying that this intuitive meaning is a bit of a chimera. And as I say, it was pointed out a long time ago in early days of AI when these kind of graph structures were also quite popular. And in particular, this was an example from a paper from that era where Quillen was asking the question, what does this triple in the graph really means? And we could have, many different intuitions about what that means. It could mean all cats are black. Maybe it means some cats are black. He even said that, well, if we wanted to be really difficult, we might interpret it as saying, if it's black, then it's a cat. So, the intuitive meaning might not be all that easy to actually agree on. And we can see how that sort of bites us in a way when we think about a query like against this example graph. So we might have a query, tell me all the architectural structures that are located in the EU. And somehow intuitively, when we look at that graph, we think we ought to be able to answer that. We can see we've got architectural structure there. We can see we've got the EU there. We've got locations and so on. But actually, we as human beings can probably do that, but computationally it's not super obvious how I would do that, or if there's even enough information in this graph to really answer that computationally, the answer is probably no. For one thing, intuitively, when we have these sort of class hierarchies, we might sort of infer that if a building, if something is said to be a kind of a tower, and I said that a tower is a kind of an architectural structure, then that thing is also a kind of an architectural structure, you know, this kind of hierarchical business. But actually, that's not really explicit there in the graph. I have to sort of know that this type relationship is sort of transitive. And actually, I need a bunch more complicated knowledge about the relationship between some of the other properties in the graph, like location, capital, member of. I have to know that, you know, if something is located in the capital of a country, then it's located in that country. That's sort of knowledge that probably all of us share, but it isn't explicitly represented anywhere in the graph. So computationally, I wouldn't really be able to answer this query. So how do we deal with this problem? And the way that we deal with it in sort of formal graph languages like OWL or even in RDF to some extent is that we define a translation between the graph and logic, usually actually just some fragment of good old first order logic. And for the data part of the graph, that's really super straightforward. We actually give a special treatment to this type edge, and we just treat it as being a sort of unary predicate. So when I say that the Eiffel Tower is an instance of tower, then that just gets translated to this unary fact. And for all the other edges, we just use the labels as a binary predicate. And we take the triple just as a binary predicate. So this is what we get by translating all of those things into logic. And we can do something very similar with the kind of ontology part of the graph, at least this very simple ontological part of the graph that just consists of these hierarchy relationships. We can translate them all into the obvious logic sentences. And this is very nice because it basically completely resolves this question of the semantics. The semantics is just exactly what this first order logic theory that pops out of doing all that tells us. Also, once we've decided that we're going to do it this way, we can actually then start introducing some more complicated sentences to explicate other knowledge that we'd like to add to the graph. So here's a couple of examples here of how we could use that to explicate this knowledge about how location, capital of, and part of are related and how we can deduce new facts from those relationships. So then we can add that in, and also it gives us immediately a semantics for question answering. So question answering then just becomes logical entailment. So for example, the Eiffel Tower was in the answer to this query about architectural structures located in the EU, just exactly because that knowledge graph, as taken as a logical theory, entails these facts that it's an architectural structure and it's located in the EU. Okay, so hopefully, you know, that's pretty nice. It resolves all our kind of semantics angst. And by the way, we could see that as, you know, the reason for Eiffel Tower being in the answer to that query is because the knowledge graph entails these two additional edges that are not explicitly represented there, but they're entailed. Okay. Oh, and yes, I promised about coming back to views. So we can also think of these kinds of rules that we can introduce as being very closely related to views. And we could even introduce another rule here that sort of basically materializes our query about architectural structures located in the EU into a new predicate called EU structure. And this is very similar to what we might do with a view in a relational database. And we can use it for all the same purposes, things like security and integration and restructuring the data. In fact, in some ways, it's a more powerful mechanism because we can even deal with recursion, which typically databases don't support. Okay, so, and yeah, another thing is we can go to the library and get, some book that will tell us how to build a system to do these kinds of the reasoning tasks. So we can go and, pick our favorite algorithm. We might decide we want to do some natural deduction or something, but there are a ton of algorithms out there that we could choose from, or even implemented systems. And we can actually find, we don't have to do it ourselves, luckily, but some kind logician has already proven to us that this algorithm is completely correct. It's guaranteed to produce all and only the correct answers to our query. So, we don't have to worry about that. We just have to worry about, if we want to implement it ourselves, we have to worry about correctly implementing it. But typically somebody already implemented it, so we can even just go with that. So, problem solved. We've got our knowledge graphs, which have all these nice features. We translate it into logic. We just do logical reasoning, which does all our answers, any question we may happen to have, and guarantees to answer it perfectly. We're good to go. Well, no, unfortunately, it's never quite so simple because there's always the issue of scalability. And, in the very early days of AI, actually, this is sort of exactly the point that they got to. We can do everything translate everything into logic, and it all works wonderfully on these little toy examples, and it's super nice. But, does it really scale up to these kinds of large scale application that many of you guys are working on? And well, the answer is, in general, sadly not. Because as we know, as Alan Turing showed us, there are actually many problems in computer science which are even undecidable. So, we can't write any program that will always guarantee to terminate with the correct answer. And indeed, first order logic reasoning is a well-known example of one of those problems. And even if we pick some kind of smaller logic, maybe it still has very high complexity. So, in realistic cases, it just takes infeasibly long to answer our questions. So what do we do? Well, first off, we have to bear in mind these are sort of worst case results. So these complexity results show us that, well, it could be the case that, it would take exponentially long or whatever to answer my query. It doesn't necessarily mean in real applications that's actually what's going to happen, because quite often these complexity results rely on sort of strange structures of data and knowledge that never occur in practical cases. But also another way, so we could just, say, oh, well, it'll all be okay on the night. But actually, with some of these large scale biohealth ontologies I've seen, it is really a serious issue. And we can't just sort of shrug and say it'll all be fine. But another way we can go is that we can study KR languages and try to find some sort of sweet spot that has, good expressive power that allows us to describe the things we need to describe in our application, but that has better computational properties. And we can try to design good algorithms to work with such logics that, again, may not have better worst case behavior, but have better typical behavior, particularly in our realistic data sets. And we can develop highly optimized reasoners that use those algorithms. So this is actually where description logic comes in. This is actually the exact motivation for research in description logic. It's a family of KR languages. They're mostly subsets of first order logic, not always, but mostly. And basically the way it works is that you have a whole bunch of different constructors like and, or, not, some kind of restricted, existential, and universal, usually counting, a bunch of things. And you can basically go along, this is like a buffet, and you can say, oh yeah, I need and, no, I don't need or, I won't have that, I'll have a bit of existential, thank you. And then when you get to the, to the till, you weigh that, and it says, oh, that'll be, X time complete, please. So you can sort of choose what constructors you want. And within the description logic community, there's been this investigation of all kinds of combinations, so you pretty much know what you're going to pay for that in terms of computational complexity. And I mean, the other thing that went on there was once this was very well understood, people sort of tried to identify combinations of constructors that were sort of hit some sort of sweet spot, and for which very effective reasoners could be built. And I guess in this community, this OWL-EL language, which comes from a description logic that was called EL, is based on that. This is an example of a case in point where people found that combination of constructors, sort of explored how they could extend it to a point where reasoning was still polynomial and you could still build these very effective reasoners. But it still has a reasonably good expressive power that's appropriate to many biohealth applications. And for that reason, because there was so much known about the language complexity, and because there were quite a number of practically effective reasoners already available, then the W3C, this was what made the W3C decide to base the OWL language on a description logic. Okay. So I just want to say a little bit about applications, because particularly in this community, it seems that a lot of the applications are what I would call ontology centric. So the main interest is developing large and complex ontologies, and the reasoning is typically used to enrich the ontology with implicit subclass axioms, and to check to make sure, to try to sort of quality assure the ontology by checking that it's at least consistent, and, maybe checking a bunch of other things. There are quite a lot of reasoners around, particularly reasoners for this EL language, one that we developed initially at Oxford called ELK, and another reasoner called Hermit that covers the larger OWL language. And these are still quite widely used, even though they were developed quite a few years ago. And yeah, there are a whole bunch of ontologies. I've heard a lot of talk today about different ontologies being developed. BioPortal is a resource. Maybe there are better resources now. I'm a bit out of touch with what's going on, so sorry if that's the case. But anyway, there's a large number of ontologies in there. SNOMED is a very well-known example of a large ontology where they use reasoners to help to develop the ontology and improve the quality. But when these ontologies are kind of deployed in applications, if that's really the case, then very often only the class hierarchy is really used at that point. The sort of rich descriptions that are used for classifying the ontology and checking consistency often don't make it into applications where you're kind of reasoning about data and so on. And in particular, I know that this is the case with SNOMED, that actually the SNOMED guys have this incredibly rich resource of knowledge about the classes described in the ontology, but what they give you if you ask for, an export of SNOMED is typically just the class hierarchy. Okay, so we'll have plenty of time for questions at the end, so you can shout at me and tell me I'm totally wrong if you don't agree with that. But that's the way it seemed to me. A lot of applications here were focused on the ontology, but that's fine. But there's also another kind of application, which I'd call a data-centric application, where actually we're mainly interested now in kind of query answering over a very large data set. So some of the examples I have from this, come from more from industry. Like we have a customer for the company, which is Festo, which is a German manufacturer of production line equipment, and they have sort of a huge number of components, and they have an ontology which tells them about compatibility between different components, and they use that in the design of production lines for a customer. And then they would query that basically to try to make sure that the system they're building is actually going to work. But we could equally well think, again, sorry, this is a bit naive. You can tell me what sorts of data-centric applications you might have more in the biohealth area. But obviously, there's a huge amount of actual data out there about patients, hospitals, physicians, cells, proteins, whatever. And maybe, some of those we'd really like to ask queries over the data, structured queries over the data that take into account the large data sets as well as an ontology. And you'll notice there's a massive difference in scale here. So typically, even very large ontologies don't get beyond tens or hundreds of thousands of classes. But large data sets can obviously, be billions or, even much larger than that. But, tens, hundreds, thousands of billions of facts. So big difference in scale, and a big difference in how you have to do the reasoning tasks to cope with those scales. So yeah, a problem with these data-centric applications is that the reasoning technology behind systems like Hermit and ELK typically just don't scale to query answering over these data sets with billions of facts in them. So in OWL2, we revisited the OWL standard and introduced 3 profiles, which are sub-languages that are exactly working the way I said before. You pick a subset of the constructors that fits with a given kind of target application area and that has a better computational complexity. And 3 profiles were identified. One, QL, which is based on the DL-like description logic, RL, based on a kind of fragment that allows for translation into kind of logic programming rules, and EL, which is based on another description logic I already mentioned. And these different profiles, as well as having good theoretical computational properties, they allow for different kinds of algorithm that are appropriate for either classification, ontology-centric applications with very large ontologies like this ELK reasoner, or there are other algorithms that work well for this query answering task with very large sets of data. I'm just going to say very briefly about a couple of those, how they work, not, intended that you should learn enough from this that you would, run off home and write your own reasoner, but just out of interest, because again, I want to come back a little bit to a few things that follow on from these techniques. So query rewriting, actually, probably all of you are really sort of familiar with that to some extent, because my impression is this is actually the way a lot of the applications in biohealth work when using these hierarchical exports from knowledge bases like SNOMED. So basically all you do here is you sort of use the class hierarchy to rewrite the query. You use the ontology to expand the query. So for example, if we have this query for architectural structures, and we know that towers and buildings are both kinds of architectural structure, we just rewrite the query by expanding it to say, yeah, give me all the architectural structures, but also give me all of the towers and also give me all of the buildings. And it's fairly easy to show that I'm done. Actually, that query will give me exactly the same answer over the data, ignoring the ontology, as the original query would have done if I'd used one of these logical fancy-pantsy reasoners that does all of the whole business together. So I can solve it all with this query rewriting. And in a lot of cases, I think that's what people are more or less doing. They kind of follow the hierarchy down, you know, they retrieve all of the subclasses and pull that together, and that's my answer. So this is basically just query rewriting. And I mean, the other nice thing about that is that it's designed in such a way that I can even translate this rewritten query into SQL and execute that over data sources that are in legacy databases. The downside of that is that I can only do it if I have a very simple language. And in particular, I can't deal with recursion because that would lead to an infinite rewriting. The other way to go is an approach called materialization, and this is just exactly the opposite. I use the ontology to rewrite the data in such a way that I can ask the original query over the data and get the same answer I would have done if I'd done the full reasoning thing. And basically, I just treat the ontology as a kind of set of rules that imply new edges, and I just keep materializing these new edges till there's nothing left to do. I'm saturated. So I can carry on doing that. And eventually, we can easily prove that eventually this will stop. I'll have materialized all the edges that there are to materialize. And then I can just ask my original query over that materialized data, and I'm getting the same answer as I would have done if I'd done this full reasoning thing. And the advantage with this is we can deal with a significantly more expressive language than we can with query rewriting. In particular, we can deal with recursion. Okay. One of the things I said I was going to come back to, which is one of the disadvantages of this approach. I guess there are a couple of disadvantages. One is, of course, you're blowing up the size of the data, and that can be polynomial in the worst case. So, that could be a problem. Typically, it doesn't seem to be too serious a problem. So in all of the examples I've seen, the biggest blow up is usually, 3 or 4 or 5 times. That could still be a problem. But anyway, and doing that materialization, of course, that can be expensive as well. Again, polynomial in the worst case. And the other disadvantage is, well, what happens if the data changes? So I can do this materialization offline, which is a nice thing. I can do that ahead of time, saturate everything, and then I just have to do these simple query answers against the data, against the knowledge graph, against the augmented knowledge graph. But what happens if I retract a fact, like, if the UK leaves the EU and I retract that fact? It's a bit complicated because I may have added in some other edges that were only there because of this fact. And so I have to do some sort of complicated process of sort of what used to be called truth maintenance. And most reasoners don't support that. Actually, if you retract any facts, they just dump all of the edges that have been added in this saturation process and do the whole thing again from scratch, which could be very expensive. And even more tricky if you want to actually change the ontology. What if I retract some axiom from the ontology? Then the truth maintenance task becomes even more difficult. I just very briefly, I haven't really got time to say much about this, but the other nice thing about materialization is that we can even use that for query answering in EL. So there's a very nice approach where we can take the EL ontology, we translate it into an RL ontology that's strictly stronger than the EL one was, basically by skolemizing existentials. we answer our query with respect to that ontology using, say, materialization. And then there's an extra step we can do called filtration, which throws away all of so the ontology is stronger when we've done that. So we may get some extra spurious answers. We'll definitely get all the good answers, but we may get some extra answers that are wrong, actually. But there's another polynomial process we can use called filtration, where we can throw away the spurious answers and guarantee to be left with just the correct answers. So we can use this materialization-based approach also with EL ontologies. And that was one of the reasons I mentioned that, was to come back to this ontology-centric application thing. So it may be in some cases that with these ontology-centric applications, actually, you really are only interested in the ontology. It's a way of formalizing and sharing knowledge, and that's actually all you want to do. But if it's the case that you really want to use this ontology to also kind of support complex queries over data sets, then it might be worth thinking about some of these reasoning approaches that can support that. Either query rewriting, if we're in a relatively weak language, or materialization oblique the combined approach, if we're using a more powerful language like EL, for example. And it would be interesting to see how that worked out in practical cases. I haven't seen it done too much in this space anyway. So yeah, I'm just going to finish off. It's all right if I take another? Perfect. So I'm just going to finish off by explaining how we got to developing this RDF-OX system and what some of the interesting issues that we encountered there were. So basically our motivation there was this materialization-based approach seems quite inviting. You can have a reasonably powerful language. This RL language allows you to express quite a lot of things. And query answering can be very fast because you can do all of the hard work materializing offline ahead of time and then answer any old question you have without having to do any complicated reasoning. But as I already mentioned, the challenges are that it can be costly in time and memory, and also there's this issue of maintenance if the data changes. So what we decided to do with RDF-OX, we addressed the first issue by building this highly optimized materialization engine that exploits multi-core architectures to provide very high parallelization when you're doing the materialization step. And then also we designed it from the beginning to support incremental maintenance of the materialization. So in RDF-OX, you can retract facts, you can even retract rules, change the ontology, and it incrementally updates the materialization rather than just throwing everything away and starting again. So the final challenge that in some ways for me was more interesting was once we built this RDF-OX guy and, we were super happy with that, it's working really well in the lab and we can cope with these like really large scale things and run all these benchmarks, everything's great. Surely, people will be just beating a path to our door wanting to use this reasoner. Well, it turns out in practice, things are a bit more tricky than that. So typically when we build these things in research, we just do the sort of minimal proof of concept thing. And of course, it turns out in real applications, people typically need a bunch more stuff. Often what for us were the least interesting things, but for them are the most important things. Top of the list for this kind of thing is numbers, strings, dates. You need a whole bunch of reasoning things that can cope with those, including stuff like aggregation, so you need to be able to have a rule that computes the average, weight of a thing, or the total weight of a thing being the sum of all of the weights of its parts, this kind of stuff. I could mention a whole bunch of things: constraints, negation as failure. Another thing that's interesting is that OLRL actually only allows for a rather simple sort of tree structured rule. But once you've got rules, it's often useful. And again, particularly in domains like biohealth, where we're often interested in complex interconnected structures like anatomy, it's useful to be able to have more arbitrary rules that can make kind of cyclical connections between things. So it turned out we had to build a whole lot of stuff, extra stuff. Oh, and the other thing, system architecture. So yes, you go, to your potential customer and you tell them, yes, this is what we've got. We've got a better reasoning engine, a Sparkle API, and a command line interface. And they say, but we really needed this thing that has all kinds of additional, security, persistence, connections to databases, blah, 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 blah. And I think we set up the company in 2017, and we weren't really ready to actually sell anything to anyone till at least 2020. It took years to build all that stuff. But you can only really do that in a company. You can't get Research Council grants for building this kind of stuff, but it's absolutely critical if you're going to deploy these systems in, real applications in industry and probably in healthcare as well. Yeah, so we set up the company, it did that. And so I just wanted to finish off just saying something about use cases, just a couple of examples, and then I'll open up to questions. So, of course, I can't not mention healthcare and life science use cases. I'm afraid I'm a bit out of date in this community. It's a while since I've really looked at all of the great stuff that you guys are doing. So probably you can tell me about a whole bunch of much more current and interesting applications than these, but these are some of the ones that I know about. Maybe it's more interesting for you to mention some applications that maybe you don't know about. So one that, of course, we're really super proud of, I think it was mentioned in the intro that we were acquired by Samsung. And the reason they did that was they wanted to use RDFOX running on the phone to power this kind of personal data, what they call the personal data engine. And basically, it's under the hood there, helping to support stuff like the daily brief and other integrate data from multiple applications. So actually, if any of you have got a 2025 Samsung phone in your pocket, you're running RDFOX there on your phone. You didn't know it. I already mentioned this configuration management application, which is a kind of interesting one because I don't think it's, so far away from many applications you might find in this domain, where you have a kind of complex ontology describing the structure of the domain. So it's not so different from things like human anatomy and cell biology, only in this case, it's kind of production line system anatomy and biology. And then you use the reasoner to sort of check whether or not a given design is actually consistent and will do the job it's supposed to do. Another application that we had that was, more directly connected in this space was regulatory compliance. This was actually with a healthcare company in the US who wanted to check that their kind of treatment of patients with diabetes was actually meeting regulatory requirements coming from the health department, one of which says something like, you need to have an eye test at least once a year or something like that, because diabetes can affect eyesight. So there's a whole bunch of these regulations, and they didn't really have any good way of checking whether the care that they were giving to patients was really compliant with these regulations. Okay, so that's all I've got to say, really. Summary. KLs are a powerful tool. There's a whole bunch of applications, technical challenges, but I think we're at the point in development of systems where at least we have, systems that, of course, you can never fully overcome these technical challenges, but address them sufficiently to make them useful in real applications. It's interesting to say the solutions came from a combination of foundational research and systems engineering. And I think it's really important to emphasize that, to make these kinds of system work in practice, there's a hell of a lot of engineering that's just as important as the foundational research and just as difficult in my experience. And by now, I'd say this is a mainstream technology that's powering industry scale applications in a diverse range of applications. I've got the usual thank you to, funders and a whole bunch of colleagues that I've worked with over the years. I didn't even, sorry, Carol, but I hadn't even clocked that you were the general chair of the conference. But you're there, you're there, and I didn't put you there, because I saw, oh, Carol's general, you were there already. So Carol, one of the many people that I had the pleasure of working with over the years. And that's it. I'll be happy to take questions if there's time for that.
So we have 10 minutes for questions. Are there any?
Fantastic talk, Ian. And I think you're absolutely spot on all your kind of estimation of where we are with the biomedical ontology community, the kind of patterns that we use for kind of materializing inferences and so on. So my question is, you were instrumental in a lot of these semantic web standards like the web ontology language, which have been hugely influential. Even though most of us are only using RL, Datalog, EL, we're now at a stage where there's a new kind of like generation are coming in. They're using labeled property graphs, and there's no standards and there's no semantics. So based on your kind of like experience of what worked and what didn't, and what you see, presumably your customers are very interested in this kind of technology as well. How do you see the kind of like the needs in the standards landscape over the next 5 years or whatever?
Yeah, thanks, Chris. Good question. I mean, I can see that label property graphs, have some good features. I do think that standardization is really important. I mean, the other thing I didn't mention about, going to customers and trying to sell them on the technology is that they actually do value that, not because they really value the standard per se, but because if they go with something that's a standard, they feel less locked in to a particular vendor. And we've definitely got several customers who explicitly went for us because of this standard support and actually avoided other people that were trying to sell them, complete solutions to all their problem, but then they would have been totally locked in. And so I think these property graph people should think about that and try to come to an agreement amongst themselves about the standard and semantics as well. What does it all mean?
Other question?
Hi, Ian. Fantastic talk. I've just got 2 questions. So one is on, as you're building the knowledge graph, a frequent problem we have, especially in the biomedical and healthcare domain, is that we need qualification statements for the nodes and properties. So for example, if we say a particular drug causes a side effect, there's going to be another 100 articles that says, no, it doesn't cause that side effect. So how do we qualify those directed edges to say, this is a positive relationship and we have another 10 negative relationship, which one do we weight? And sometimes the need to capture both the positive and negative relationship is important for reasoning over that graph. And the other question, and again, if you permit me and indulge me, what we see is we have people building knowledge graphs, but what we as a community need is a community knowledge graph where everybody has an expertise in, let's say, diabetes, to build their own knowledge graph for diabetes, and somebody else comes along and here's the cancer knowledge graph. So how would you recommend to us as a community to build a community knowledge graph so the graphs can be integrated together and can be reasoned over together?
Okay, thanks for those two good but tricky questions. So the first one, the language that's supported in OWL and RDF doesn't directly support any of that, so there's no way to add weightings on these edges explicitly in the language. Of course, you can sort of build graphs that have that in a more complex way, because you can do some sort of reification that means you can have more kind of properties attached to the edge, and then you can have rules which somehow reason about that. But it's a lot more kind of DIY. So down the line, you're far more likely to run into these integration problems that you alluded to with your second question. I'm not sure what the answer to the first one is, other than having some extended standard that tells you how to do that. So at least it's interoperable. And then as far as the second thing is concerned, I came to the conclusion a while ago that I'm sort of suspicious of efforts to build ontologies for ontology building's sake. I think what you need is some application focus that says, okay, we have an application, this is what we want to do with it at the end, and then we build the ontology that works for that application. If it works for other stuff as well, great, but the main thing is it needs to work for that, and that could be the sort of focus, how you bring these disparate groups together, maybe.
Other questions? I've got one question. I know you stayed away from LLMs during the presentation, but I'm just curious if you've used them in the sense of like your example with the Eiffel Tower and the shard. So you had the nicely written word location, right? And so you interpret that, but what if it was LOC, right? Like maybe that's a good synonym for location that somebody used in one of these ontologies, and to use LLMs to kind of interpret that and to help some of this the reasoning that occurs. Have you ever?
Yeah, I mean, that's a good question. And actually, a lot of our more recent work in the group at Oxford has been about this very issue of knowledge engineering, which is still, I would say, by far and away the biggest sort of barrier to using these kinds of systems. Capturing this knowledge is really hard. Integrating knowledge from multiple sources is really hard. And LLMs can definitely be a huge help in that, trying to identify these sorts of synonyms or relationships between different terms, trying to identify missing knowledge in the graph, trying to identify incorrect knowledge in the graph, just generally trying to lubricate this process of knowledge construction and curation. I think there's a massive opportunity there. I also think it's worth mentioning there's a massive opportunity the other way around, that knowledge graphs, curated knowledge, can be, hugely important in applications that are using LLMs to, try to avoid some of the, less desirable features. And there's a huge amount going on there with RAG and so on these days. So I think there's a lot of kind of synergy there between the two different approaches that hopefully will be more and more exploited in the coming years.
Thanks.
Yeah, thank you very much for this talk. I wonder, how much do you have to deal with inconsistencies in your knowledge? Because especially when you integrate data from multiple sources, it's quite likely that you get actual inconsistencies when you have data. And once you have an inconsistency and you materialize, you get a complete graph. So how can you still give useful answers when you have inconsistency in your data?
Yeah, so it's a good question. I mean, actually, I have to say, in quite a lot of the applications in industry, it doesn't really arise so much because they have fairly well curated, local data already. But actually, I would say that this inconsistencies arising is a sort of feature, not a bug. So we put things together, we have our idea of the mapping, we run the reasoner. Oh, it's inconsistent. Well, then, clearly there's something probably that we should be looking at somewhere. And actually, we can use the reasoner to identify where that is. I mean, more or less, moreover, in rule-based reasoners in particular, having some inconsistency somewhere doesn't actually stop you from doing reasoning. Yeah, in principle, you have this idea that everything is entailed, but you can quite easily use these rule-based reasoners in a way that they just derive the fact false somewhere, but you can still carry on and do everything else as you would have done it before. You know that once you've derived this fact false somewhere, that you have to be careful, but you can investigate where the source of that was and hopefully fix it. So in general, as I say, I'd say it's a feature, not a bug. It tells you, points to where there's something wacky going on that I should look at more closely and, decide what to do about that.
I think that we need to move to the next talk, but
We had an
Oh.
online question.
yes.
It says, can you ask Ian about reusability of an ontology? I fully agree with building an ontology focusing on the use case.
Yeah, well, I mean, I guess I didn't have too much more to add to what I said before, which was that I think you should build an ontology with some use in mind. Of course, you can try to follow sort of best practices, and actually within this community, there's been a huge amount of really good work on best practice for ontology design. And if you do that, it's much more likely that your ontology will be more reusable, more easy to integrate with other ontologies. But that should be a bonus, rather than necessarily the main event.
Okay, thanks. Okay, so clap. Yes. Let's thank our keynote.
Thank you.